Hello and welcome to today's revision session looking at the concept of motion for the forces topic in GCSE Combined Science Physics. So what we're going to look at in today's revision session is we're going to look at Newton's laws, motion graphs and the equations of motion. So first topic we'll look at is Newton's laws of motion. So these are three laws which Isaac Newton worked out to determine the movements of all objects in the universe. Law 1, which we call the law of inertia. All objects will travel at the same velocity, which we call inertia, unless it's acted upon by a resultant force. A resultant force causes acceleration. Now remember, inertia is the tendency for objects to remain at the same velocity unless a resultant force acts on it. So a resultant force is an overall force on the object. So the resultant force is the combination of forces on an object. So we can calculate the resultant force by finding the difference between the two forces acting on the object. So for example, in this situation, we have 20 newtons up, we have 10 newtons down, so the resultant force is 10 newtons upwards, 20 minus 10. Now this is because one force is considered negative because it's moving in the opposite direction, so we give it a minus sign. Now the length of the arrows in a diagram help you understand the value of the forces. So you can tell that the arrow going down is smaller, so that's going to be the smaller force. So the resultant force can replace the other forces in a diagram. So the number of forces acting on an object can be replaced by a single force that has the same effect as all the original forces acting together, which we call the resultant force. So objects accelerate in the same direction as their resultant force. So in this example, the object accelerates upwards. Now the second law of motion is that force is equal to mass times acceleration, where our resultant force is in newtons, our mass is in kilograms, and our acceleration is in meters per second squared. The size of the acceleration depends on both the mass of an object and the resultant force on the object, which is basically the mathematical interpretation of the first law of motion. So this indicates the two factors that affect acceleration, the resultant force and the mass. So acceleration is directly proportional to resultant force. Double the resultant force, double the acceleration. So we get a straight line through the origin if we plotted a graph of acceleration against resultant force, because a graph which is a straight line at best fit through the origin indicates direct proportionality. But acceleration is inversely proportional to the mass of the object. Now the full name of mass in this context is called the inertial mass. Now inertial mass is a measure of how difficult it is to change the velocity of the object. The larger the inertial mass, the harder it is for an object to change velocity, so the harder it is to accelerate, because inertial mass is the resultant mass divided by acceleration. So the inertial mass is the ratio of the resultant force over the acceleration. The larger the inertial mass, the greater the resultant force you would need for the same acceleration. So the larger the inertial mass, the greater the inertia of an object. Now law 3 is that when two bodies interact, they exert equal but opposite forces on each other of the same type. So this gives each object, both objects, a resultant force. So it makes both objects accelerate. So for this law to work, you need two objects in a system. So for example, the person and the ground. Okay, and the forces are equal in size and in type, so the same type of force, but they act on two different objects and act in opposite directions. So the law produces the same resultant force on two different objects. Now these two objects could accelerate at different speeds, different rates, my apologies, if objects have different masses. So let's just recap what we've learned so far. Law 1. All objects travel at the same velocity unless it's acted upon by a resultant force. A resultant force causes acceleration. Law 2, resultant force in newtons equals inertial mass in kilograms times by acceleration in meters per second squared. And then law 3, when two bodies interact, they exert equal but opposite forces on each other of the same type. Now to fully understand the implications of Newton's laws of motion, we've got to draw free body diagrams of an object which show us the forces acting on an object. So in a free body diagram, you always draw your forces from the center of mass, which tends to be the center of the object. Now in your diagram, you always show the direction the force is acting in with an arrow, and you show the size of the force with the length of the arrow. So it's also you clearly label the type of force with the appropriate label. Now in your diagram, you should be able to work out the resultant force vertically, if there is one, and horizontally, if there is one. So this is an example of a free body diagram. This is an example of a free body diagram. So how do you draw your free body diagram? Use a ruler and a pencil. Use an arrow where the size of the arrow shows the size of the force. Use an arrow where the direction of the arrow shows the direction of the force. And add a label to your force to indicate the type of force present. So for example, this free body diagram shows two different forces acting on the body, reaction acting upwards and weight acting downwards. Now you can then equate the forces to work out your overall force or your resultant force, and remember, resultant force causes acceleration. This acceleration happens in the same direction as the resultant force. In this example, because the arrows are the same size but in opposite directions, you'll see that these two forces cancel out. There's no resultant force, the object will not accelerate. So in this example, we can actually put values on there. So if it's 70 newtons forward and 40 newtons backward, the resultant force is 30 newtons forward. So this can only be done if they're in the same plane as each other, either horizontal or vertical. Now we say 40 is minus 40 because it's going backwards. It's the opposite direction. Now if there's a resultant force, the object accelerates, and it accelerates in the same direction as the resultant force. And to accelerate means to either change speed or change direction. So what have we learned so far? When two forces acting on an object are not equal in size, we say they are unbalanced. We have a resultant or overall force. A resultant force on an object will make an object accelerate. The object accelerates in the direction of the resultant force. This is Newton's first law of motion. So in this example, the resultant force is 100 minus 60. Why is it minus 60? Because 60 is acting in the opposite direction. So resultant force is 40 newtons forwards. Okay, so that's how it works. The object accelerates forwards. This means the object can either change speed or change direction. And we can calculate the size of the acceleration by using Newton's second law. Acceleration is resultant force over inertial mass. So in this example, resultant force is 40, inertial mass is 400 kilograms, so it's 40 over 400. The answer is 0.1 meters per second squared. So this means, like we said before, the larger the mass, the lower the acceleration for the same resultant force. So the size of an overall force acting on an object is called the resultant force. If the forces are balanced, there's no resultant force, and the resultant force is the difference between the two forces in opposite directions. If there's a resultant force, the object accelerates in the direction of the resultant force. Next topic, a motion graph. Now, speed is a quantity measuring the distance an object covers in a certain time, and there are many different measurable speeds in the world, and you've got to remember a few of these for your exam, such as the walking speed, 1.5 meters per second, the running speed, 3 meters per second, the cycling speed, 6 meters per second. Now, speed does not involve direction, it's a scalar quantity, but the speed of all objects stays constant. The speed of an object throughout the journey is rarely the same, so we calculate an average speed. Now, the speed of a human walking or running or cycling can depend on factors like age, terrain, fitness, how far you've travelled. Now, objects can vary in speed not just as humans as well, though, because sound can change speed, wind can change speed. So that's very, very important. But how do we calculate these speeds? Well, speed in meters per second is distance travelled in meters over time taken in seconds, which is an equation you must memorise for your examination. And you've got to be able to rearrange this equation and work out the units. Now, the units of speed are the units of distance divided by the units of time. Now, this is the equation used to work out the average speed of an object, because objects rarely stay at the same speed. Now, if you have constant acceleration and the object is starting from rest, the final speed is always double the average speed, because the average speed is the middle value of speed for your journey in that instance. So that's a very important idea. So We can also plot this on a graph as well. So if an object moves along a straight line, the distance travelled can be represented by a distance time graph. So we're putting distance on the vertical axis and time on the horizontal axis. And the speed of an object can be calculated from the gradient of its distance time graph. Now a gradient is the change in the y value divided by the change in the x value. So it's going to be change in distance over change in time. Now when calculating the gradient, always draw a gradient triangle as it shows the values you're using. Now the gradient triangle should be as large as possible, as the greater the range of values used, the more reliable the result. But this method can only be used if an object has a constant speed, because it'll have a straight line of best fit. Now, in this example, you don't actually need to draw a line of best fit. You plot from point to point to point, because you're showing a journey of an object, not working out the trend. Now, if an object is changing speed, the line of a distance time graph will be curving. So if it's curving upwards, it's accelerating. If it's curving downwards, it's decelerating. Now, if an object's accelerating, the speed at a particular time, the instantaneous speed, can be determined by drawing a tangent and measuring the gradient of the distance time graph tangent at that point. So a tangent is a straight line that touches a curve at a point, but if it's extended, doesn't cross at that point. So this is the tangent at 10 seconds. It's only touching the line at the 10-second mark. You then work out your gradient of your tangent in the same way you worked out previously by drawing a triangle, and you repeat the previous calculations. Now here are the following sections on a distance time graph. If it's a straight line going upwards, it's an object moving at constant speed. If it's an object that's got a flat line, it's stationary. If the line is curving upwards, it's accelerating, and if the line is curving downwards, it's decelerating. On a distance time graph, the line can never go downwards, because distance can only ever go upwards because it's a scalar quantity, so it can't be a minus. So distance is how far an object moves, it can't decrease in the journey. Now, if you wanted to consider the direction of an object, you wanted a vector quantity of distance, you would actually use something called displacement, which is the straight line distance measured from the start point to the finish point of the journey in a straight line. Now displacement is a vector, so if a distance time graph is a line going downwards or is negative, that's not a distance time graph, that's a displacement time graph, which is a very important idea. Now this leads us to two different quantities. First, you've got the velocity, which is the speed in a given direction. Now velocity is a vector quantity, and vector is the rate of change in displacement of an object. So velocity is the change in displacement over the change in time, and we can represent direction with the plus or a minus sign, while speed is a scalar quantity. Speed is the rate of change in distance of an object. So speed is the change in distance over the change in time. It doesn't have a direction, so it must be a positive value. Now the velocity is a much more useful quantity than speed, as it contains more information. So imagine two cars travelling head-on. They're travelling in opposite directions. You get a large impact force. Why is that? Because the change in velocity is very large. Because now we're considering the direction. Because one is in the opposite direction, it must have a negative sign, so the difference is very large, 61. However, if it's in the same direction, if it's back onto someone else, okay, the velocities are both in the same sign, so they're both positive or they're both negative. So now plus 30 and plus 31 means the difference is only 1. So because it's a small change in velocity, because we've considered the direction, it means the collision is less forceful. So it's a very important idea. So velocity is the speed of an object with a direction or the change in displacement. A quantity in physics with a direction is called a vector. We can illustrate velocity by either stating the direction of travel with a plus or a minus. You can decide which direction is positive and negatives, but they must be opposites of each other. So if we say right is positive, left is negative. If we said left is positive, right is negative. If we said down is positive, up will be negative. Now if an object is moving in a circle, then it can have a constant speed, but it must have a change in velocity, because velocity is a speed in a given direction. And if an object is moving in a circle, it's changing direction, as shown there. So it means it's changing velocity. So it's accelerating. Now, we can show the velocity, how it changes an object by having a velocity time graph. Now here the velocity is on the y-axis and the time is on the x-axis. So what is the gradient representing? Well, the gradient is representing the change in y over the change in x, the change in velocity over the change in time, which is known as acceleration. So the gradient of a velocity time graph is acceleration. So that's a very important idea. Now, if an object is changing its rate of acceleration, the line of velocity time graph will be curving. Now, again, you can work out the gradient by drawing a tangent like before in working out the gradient of the tangent. Now, the following section on the velocity time graph represent the different types of motion. A straight line up means constant acceleration. A flat line means constant velocity. Now, it can only be stationary if that flat line is actually on the x-axis because I have a constant velocity of 0. Then you've got a line going down, which is constant deceleration. Then you've got a line below the x-axis, a negative, which is constant acceleration in the opposite direction, because minus means you're going in the opposite direction. So if you calculate the acceleration of an object and it's negative, it could either be deceleration or acceleration in the opposite direction. Now, to work out which one it is, you've got to look at the velocity time graph or look at the actual object itself. So that's a very important idea. But what do we mean by acceleration? Now, acceleration is the change in velocity over a certain time. A velocity is both a speed and a direction. So an acceleration is either a change in speed or a change in direction, because acceleration, like velocity, is a vector quantity. Now, we can work out acceleration with the following equation. Acceleration in meters per second squared is equal to change in velocity, meters per second, over time taken for the change in seconds. So these two equations are the same way to write that equation, because change in velocity is final velocity minus initial velocity. And once again, this equation needs to be memorized for your examination. Now, the acceleration is measured in meters per second squared because we're doing meters per second divided by seconds, so it's meters per second squared. Now, the fundamental rule of physics states that an acceleration is caused by a resultant force. No resultant force, no acceleration. Newton's first law of motion. So acceleration can only occur when there's a resultant force acting on the object. Now, velocity is speed with direction, so if you change speed, you accelerate. So if an object changes speed, it's changing velocity, it's accelerating. So you need a resultant force to do this. That's the most commonly thought of method of acceleration. And negative acceleration in this context could be a decrease in speed. Another way is that velocity is the speed of the direction, so if you change direction, you change velocity, you accelerate, which once again requires a resultant force to do this. Now in this example, a negative acceleration could mean moving in the opposite direction. You only know which one it is, change of direction or change of speed, by looking at the information in the question. But to produce either, you need a resultant force. Now like we said before, whilst the gradient is the acceleration, the area under a curve is the distance travelled by an object. So to work out the area under a curve, you split your area into different shapes, triangles, rectangles and squares. So you split them up into those, you work out the area of each shape, so a square is length times by height, triangle is a half length times by height. You then add all the values together, you get your total area. So in this instance, we break it up into different sections. We then work out the areas of the different parts as such like that. We then add them all together to get our total distance travelled, as shown in this example as well. So we can actually have velocity time graphs with a negative section. So what does the negative section mean? Well, the negative section means the object's moving in the opposite direction. So that's in one direction in the positive and the opposite direction in the negative. So that's a positive displacement, then a negative displacement. Now, if you wanted to work out the total distance, because distance is a scalar and has no direction, you just add them. But if you wanted to work out the total displacement, you've now got to consider the minus. So to work out the total displacement, you subtract the two areas. Now, the last bit we're going to look at are the equations of motion. Now, if you consider any object falling, when an object first falls, the weight acting on an object is larger than air resistance, So there's a resultant force downwards, so an object accelerates downwards, because the resultant force causes an acceleration in the direction of the resultant force, Newton's first law of motion. So the object accelerates downwards because there's a resultant force downwards, because the weight is much larger than the air resistance, so we've got a resultant force. So now, because we've got constant acceleration downwards, our velocity time graph is a straight line, because a constant positive gradient means constant acceleration. But as the object increases in velocity, the air resistance increases as more air particles are pushed out of the way per second, so it decreases the resultant force and decreases the acceleration, because whilst the weight is unchanged, the air resistance is now larger, so the resultant force is smaller. So the object's still accelerating, it's still getting faster, but it's going at a slower rate, because resultant force and acceleration it causes are directly proportional, Newton's second law of motion. So as the resultant force decreases, the acceleration it produces decreases. Now, always remember to talk about this stage of a fallen object's journey. So as the acceleration is slowing, the object starts to curve on its velocity time graph. The gradient of the line is decreasing, so the acceleration is decreasing, but the velocity is still going up at a slower rate. Eventually, the air resistance is the same size as the weight, so the velocity of the object stays the same. We've got terminal velocity. So at that point, the two forces equal each other. There's no resultant force, so the object is not accelerating, because when there's no resultant force, there's no acceleration. The object maintains the same speed with the same direction, so if it's already moving, it'll keep moving. Inertia. So that's Newton's first law of motion again. So we'll get our flat line here because it's now got a constant velocity. It's got a gradient of 0, no acceleration, constant velocity, the terminal velocity. Now remember, as the object falls, the weight stays constant, but the air resistance changes size in different parts of the journey. So an object first falls, weight is larger than air resistance, there's a resultant force downwards, so it accelerates downwards. But as the object increases in velocity, the air resistance increases as more air particles are pushed out of the way per second. This decreases the resultant force and acceleration. Eventually, the air resistance is the same size as the weight, so the velocity of the object stays the same, its terminal velocity. Now, if we did have constant acceleration, which wasn't the case in the previous example, we could use the equations of motion to work out values of the object moving. Now, constant acceleration can also be called uniform acceleration. So, for example, when an object is falling freely under gravity with no air resistance, that will be constant acceleration. So near the Earth's surface, any object falling freely under gravity has an acceleration of about 9.8 meters per second squared. But other examples could be a plane taking off, a train pulling out of a station, or a car on a motorway. Now there are two equations you've got to use for this. Now we call them the Suvat equations due to the terms found in the equation. S, displacement, U, initial velocity, V, final velocity, A, acceleration, and T, time, Suvat. Okay, so as a result, remember S stands for displacement, not speed, and D will be distance travelled, but we're not considering distance travelled in these equations. So, what are our two equations we've got to know for GCSE? Well, we've already come across the first one. Acceleration is change in velocity over time. So it's the final velocity minus the initial velocity over time. A equals V minus U over T, which you've got to memorise. But the second equation you're given for your examination. Final velocity squared minus initial velocity squared equals 2 times by acceleration times by displacement. Or when we put our symbols in, V squared minus U squared equals 2AS. But this equation is given to you in your examination. But you'll need to rearrange the equation to work out one of the values. So here are two Suvat equations which can only be used when an object has constant acceleration throughout its journey. So for example, falling due to gravity. Now in examination questions, it's common for you to work out the acceleration using these equations, then work out the resultant force by using the equation F equals ma. So, how do you use this equation correctly? So step 1, write out the variables that are known in the question. Step 2, select the correct equation. There should only be one unknown variable in the equation you've chosen. Then place the numbers in the equation, make sure the units are in the correct form, simplify and rearrange the equation as needed, calculate an answer, place in the correct units with the correct significant figures, and remember our assumption that the acceleration has to be constant. So let's have a look at an example. So a student's investigating terminal velocity by dropping balls of modelling clay in a liquid. For a particular ball, she makes the following measurements. Initial velocity, 0.035 meters per second. Final velocity, 0.0313 meters per second. And the distance over which the velocity changes, 0.30. What's our average acceleration? Well, we write out SUVAT, S, U, V, A, and T. Now we want A, but we don't have T, but we have S, the displacement, we have U, the initial velocity, we have V, the final velocity. So what do you then do after that? You select the correct equation. Now we use V squared minus U squared equals 2AS because there's only one unknown variable in that equation, A, because we know V, we know U, we know 2, and we know S, so we can work out A. We couldn't use the other equation because there was two unknowns in that equation, A and T. You then pop your numbers in. Now the trick is you put your numbers in first and then you simplify afterwards. You don't try and do it at first. So you put your numbers in, you work through each side until you get to a point where you're happy with taking one across the other side and you work out your answer. You then calculate your answer, placing the correct units with the correct significant figures. So we take that number on the screen, we go, right, the number given in the question is two significant figures in each one, 3, 5, 1, 3, 3, 0. Remember, we start counting our sig figs with the first non-zero number given in the question, and then we put the right units on, meters per second squared. So remember, why is it a minus? Because its object's decelerating, it's slowing down. So let's have a look at another type of question. A van is travelling at 23 meters per second. It starts decelerating uniformly at 2 meters per second squared as it heads towards a built-up area 112 meters away. What will its speed be when it reaches the built-up area? Well, the first thing you do is you write out SUVAT, S, U, V, A, and T. Now remember, A is minus 2 because it's decelerating, it's slowing down. You then select the correct equation, you substitute in the numbers, you simplify each side first. When you're comfortable that you simplified it, you take one across to the other side, you then work through your answer, then you look to yourself, well, these numbers, we've got two significant figures, 23, two significant figures, 2.0, we've got three significant figures, 112, so we go with the smallest number, which is 2, so you go, right, it's 9.0, 2 sig figs, and then we put our units in meters per second. So remember, our assumption here is this only happens if the acceleration is constant. So let's summarise what we've learned in this revision session. A resultant force is a single force that has the same effect as all forces acting on an object. If the resultant force on an object is 0, the object stays at rest or at constant velocity. If the resultant force on an object is not 0, the velocity of the object will change. If two forces act on the same line, the resultant force is the sum if they act in the same direction, the difference in the opposite direction. Distance is how far an object moves. Distance does not involve direction. Distance is a scalar quantity. Displacement involves both distance and the direction it moves in. It's the straight line from the start to the finish of a journey in the direction of that straight line. Displacement is a vector. Speed does not involve a direction and is also rarely constant. When people walk, run, or travel in a car, their speed is constantly changing. And the speed a person walks at, or runs at, or cycles at depends on their age, the terrain, the distance that they've travelled. But average distance speeds include 1.5 meters per second for walking, 3 meters per second for running, and 6 meters per second for cycling. But it's not only humans that have varying speeds. The speed of sound, the speed of wind can also vary. Distance travelled equals speed times by time. The velocity of an object is its speed in a given direction. Velocity is a vector, and motion in a circle involves constant speed but change in velocity. If an object moves along a straight line, the distance travelled can be represented by a distance time graph. The speed of an object can be calculated from the gradient of its distance time graph. If an object is accelerating, its speed at any particular point can be determined by drawing a tangent and measuring the gradient of the distance time graph at that time. Now, velocity is a speed in a given direction. Acceleration is the change of velocity per second, measured in meters per second squared. Average acceleration is calculated by change in velocity over time taken, and deceleration is the change per second when an object slows down. Now you can calculate the acceleration of an object from the gradient of a velocity time graph. The distance travelled is calculated by the area under a velocity time graph. Now, like we mentioned before, an object falling through a fluid initially accelerates due to the force of gravity. Eventually, the resultant force will be zero and the object will move at its terminal velocity. And terminal velocity is the constant speed of an object falling when it's been traveling for a prolonged period of time. Terminal velocity occurs when air resistance and weight are equal in size and the air resistance varies throughout the journey. Now, the following equation applies to uniform acceleration. V squared minus u squared equals 2as, but it only works with uniform acceleration. So if we're being successful, we've learned about Newton's laws of motion, we've learned about the motion graphs, and we've learned about the equations of motion. I hope you've enjoyed this revision session looking at these topics in the forces unit of combined science physics, and have a lovely day.